Hello everyone, welcome to the next lecture of bipolar junction transistors. In this lecture today we are going to do some examples and I hope that you will learn how all the concepts that you have learned by far, how you can apply those concepts and solve some of these example problems. We will see how we can use these bipolar junction transistors in the DC circuits and how to solve these circuits. Um, okay. Before we jump to these problems, here is a very kind of a overall very simple models of when a BJT, NPN, or a PNP transistor is or gets operated in the active region or the saturation region. In the active region for an NPN transistor, let's talk about NPN transistor first. NPN transistor for the active region and or the saturation region, emitter to base junction needs to be forward biased for both of the modes of operation, active or saturation. For the active region, our emitter to base junction again is forward biased and collector to base junction should be reverse biased. Right? For the emitter to base junction needs to be forward biased, we can replace that PN junction by a forward conducting diode, and we can replace that diode by a constant voltage drop model. So we ended up putting this voltage value over here where VBE equals 0.7 volts, which means that emitter to base junction is forward bias. And we represented the emitter to base junction over here by a 0.7 voltage source or a potential drop across it. If you remember the voltage drop model of a PN junction diode from the diodes chapter. Again, these are the common emitter models. So in order to again operate this NPN transistor, our emitter to base junction is forward biased. Our collector to base junction should be reverse biased. We saw that for a collector to base junction to be reverse biased, our collector to emitter voltage should be greater than 3 volts. Then our collector to base junction will be reverse biased and we will operate the transistor in the active mode. As soon as this voltage will drop and VCE becomes equals to 0.3 volts, this will be the edge of saturation or the boundary of saturation and the active region. And as this value falls below 0.3, it will start to go down into the saturation mode. And since our saturation mode, if this is VCE and this is collector current, we saw that our saturation mode falls very sharply. In the saturation mode, the collector current falls very sharply. So we saw that as soon as our collector to emitter voltage gets further down to approximately 0.2 volts, it's very deep into the saturation mode. So we can replace this current source over here with a potential drop over here and for the collector to emitter in between collector to emitter terminals. So our VCE saturation value equals 0.2 volts. Another difference that you can see over here from the active mode and the saturation mode is the value of the collector current, right? So our value of the collector current over here, IC equals beta times IB. However, over here we can see that our collector current equals beta forced into IB. And we know that beta forced equals IC over IB. But what happens is our base current is increasing and our collector current is decreasing. With the increase in the base current and with the decrease in the collector current in the saturation region, our beta will decrease, is less than our beta in the active region, beta of the transistor in the active region. So this is how we can operate the NPN transistor in the active and the saturation regions. Here are the very simple models. Now moving to the PNP transistor, our entire reasoning and the models will remain the same, except now we have a PNP transistor. So in order to forward bias the emitter to base junction, we are going to reverse the polarity of our voltage values, right? So now we have a VEB, it needs to be equals 0.7 volts. To conduct the emitter to base junction or to make the emitter to base junction as forward biased, and similarly our emitter to collector voltage should be greater than 0.3 volts for it to be in the active region, As soon as VEC becomes equals to 0.3 volts, it will go to edge of saturation. And as soon as this will further fall below and will become equal to 0.2 volts, this will be deep into the saturation mode. So this means that our transistor is in the saturation mode, which means that collector to base junction now becomes forward biased, right? So in the saturation mode, our collector to base junction is forward biased. Our emitter to base junction will be forward biased in both active and saturation regions. So we can use this very simple models of the BJT transistor while operating them in the DC circuits, and whether they are in the active mode or the saturation mode, we can replace the emitter to base junction with a constant voltage drop model of a 0.2-0.7 volts, and in the saturation region we can replace our voltages, our VCE collector to emitter voltage of the saturation region can be equals to 0.2 volts when it is operated somewhere in the saturation region, mostly deeper into the saturation region, and exactly equals to 0.3 volts almost equal to 0.3 volts when it is at the edge of the saturation, as it is moving from the active to the saturation regions, or collector to base junction is becoming forward bias, moving from the reverse bias to the forward bias condition. Okay, now let's move to do some examples. Now we're going to do some of the examples here today. Okay. So here's a circuit that is shown, and we want to analyze this circuit. Analyzing this circuit means that we need to determine all node voltages and all branch currents. So we need to determine the value of the collector current, the emitter current, the base current. We need to find out the value of the collector voltage, the emitter voltage, and the base voltage. The base voltage is very easy. Our base terminal is directly connected to 4 volts. So our base voltage is 4 volts. Okay. So this is easy. Now we also know that our VBE, this is an NPN transistor, so emitter to base junction is forward bias, so our VBE equals 0.7 volts. Sorry. Okay, so this means that our VB minus VE equals 0.7 volts, right? We know the value of VB, so we can find out the value of VE. VE will be equals to VB minus 0.7. 4 minus 0.7, this will come out to be 3.3 volts. So our VE will be 3.3 volts. So if we know the value of VE, we can easily find out the value of IE. So emitter current should be equals to VE over RE. VE is 3.3 volts. RE resistance is 3.0 kilo ohms. So the value that will come out to be 1 milliamperes. So the value of the emitter current will come out to be 1 milliamperes. Now we need to find out the collector voltage and the collector current. Before finding out the value of the collector current, we need to make an assumption whether we can start with any assumption. Conventionally, not conventionally, but most of the times we start with an active region of operation, and then we kind of, after finding out all the values, we verify that assumption if that assumption is correct. If that assumption is correct, okay. If that assumption is not correct, then we will again move back and change our assumption to the saturation region. So we can kind of pick this strategy for all the questions, and then we will solve these questions. So okay, so our assumption now, assume BJT is in active region. Okay, so let's assume that our bipolar junction transistor is in active region. Okay, so while making this assumption, okay, so we ended up having this assumption. Now we want to find out the value of the collector current. We know that the value of the collector current equals to alpha times IE, right? And if you remember from one of the first week lectures, our the value of the alpha equals to beta over beta plus 1. The value of the beta is 100. So it is 100 over 101, which should be equals to 0.99, approximately equals to 0.99. So I can easily find out the value of the collector current to be 0.99 multiplied by, what is IE? IE is 1 milliamperes. So collector current is 0.99 milliamperes. So we ended up finding the value of the collector current. Now I know the value of the collector current. I know value of the RC and the biasing voltage over here. So the VC can easily be found by 10 volts minus ICRC, right? So VC is 10 minus IC 0.99 multiplied by RC 4.7. Kilo and milli will be cancelled. So if you will find out this, if you will solve this equation, solve these numbers, what you're going to get is this is approximately equals to 5.3 volts. So this is the collector voltage. Our collector voltage is 5.3 volts, right? And what is our base voltage? The voltage of the base terminal is 4 volts. So we know that now our collector voltage is greater than the base voltage, and by how much amount? Delta V is 5.3 and 4, 1.3 volts. So our collector terminal is at 1.3 volts higher potential as compared to the base terminal. So this means that our collector to base junction is reverse biased and active region assumption is correct. Okay, great. So our assumption was correct. So by now we ended up finding the value of the collector current. We have a collector voltage, we have emitter voltage, we have emitter current. We want to find out, so I think the only thing that is left is finding out the base current. Now we know that our emitter current is a summation of the base current plus the collector current. So the base current should be equals to emitter current minus collector current. Right, so our emitter current equals 1 milliamperes and collector is 0.99. Right, so 1 milliamperes minus 0.99 milliamperes. So it will come out to be 0.01 milliamperes. This is the value of the base current. Again, please note that the value of the base current is very, very small. Right, our collector current is approximately equals to the emitter current. Our value of the base current, since our value of the base current is very, very small, and this condition is true in the active region of operation when our collector current again is very similar to the emitter current, and base current is very small since our beta values are very high as well. All right, so now let's do another example here. So in this example, what we want to do is we want to find out, again we want to solve the circuit. We want to find out the value of the collector voltage, the emitter voltage, the emitter current, the collector current, the base current. This is the base voltage. And we know that the value of VBE is 0.7 volts again. All right. Okay, so we're going to start exactly the same way. So what we have given, we want to analyze the circuit. We want to determine the voltage nodes, all the node voltages and the current flowing through all the branches. The base voltage is 6 volts, which is given. Another assumption is given that transistor is specified to be at least 50. So this is another parameter that is given to us. Okay, now let's solve the circuit. Again, we're gonna use exactly the similar approach. We have been given the value of the base voltage, which is 6 volt. We know that VBE equals 0.7 volts, which is VB minus VE. Now, so we can easily find out the value of VE. So VE should be VB 6 volts minus 0.7 volts. So it should be 5.3 volts. So the emitter voltage over here, this will come out to be 5.3 volts. So this is the value of the emitter voltage, or the voltage at the emitter terminal. Okay, so this is good. We can easily find out the value of the emitter current now. So our value of the emitter current will be equals to VE over RE. VE is 5.3 volts over 3.3 kilo ohms. the value of the emitter current, if we will solve this, will come out to be 1.6 milliamperes. So we ended up finding the value of, again, the emitter voltage, the base voltage, and the emitter currents. Okay, so this is good. Now, before finding out the value of, again, the collector current and the collector voltage, we need to make an assumption. Again, we will start with assume BJT is in active region. And then we will see if our assumption is correct or not, and if we need to change it or not. Okay. So in order to find out the value of the collector current, we need the value of the alpha or beta. However, since we are not provided the exact value of the beta, the statement that is provided to us is that we can assume that the beta is at least 50. Since we were not given absolute value of the beta, so we cannot use this equation, and we are just going to assume over here is that, so BJT is an active region, we are going to make an assumption that IC is proportional to alpha times IE. So this is what we know. However, we also know that the alpha is usually almost equals to 1, because our beta values are usually very larger, right? So if you remember that alpha is equals to beta over beta plus 1. So if our beta values are very larger, alpha values approaches to 1. So we're going to make this assumption that our collector current, let's say, is almost equals to the emitter current. And we are going to see if our assumption of the BJT is in the active mode is valid or not. And then we're going to find the exact values too. Okay, so over here our collector current is approximately equals to the emitter current. Okay, so what is the value of the emitter current? Emitter current is 1.6 milliamperes. Okay, so our collector current is also now 1.6 milliamperes. If our collector current is 1.6 milliamperes, I can easily solve this thing, right? So our VC now would be equals to 10 volts minus IC RC, assuming this to be RC, labeling this to be RC. So it would be 10 minus IC is 1.6 milli into 4.7 K. So once we will solve that, the value of the voltage that we get is 2.48 volts. Okay, so now we see that our collector voltage is 2.48 volts. Our base voltage is 6 volts. So our collector voltage is less than base voltage. And what is the difference? The difference is 3.52 volts. So now the base terminal, the voltage at the base terminal is 3.52 volts higher as compared to the collector in this NPN transistor, NPN BJT. So this means that collector to base junction is forward biased. And if collector to base junction is forward biased, BJT is in saturation and not active. So this means that our initial assumption was incorrect. Our BJT is not in the active region. However, our BJT is in the saturation region. Okay, great. So once we find out that our BJT is in the saturation region, so we can start with the next thing. We know that the value of the VCE in the saturation region equals 0.2 volts, right? So I can assume that this VCE equals VC minus VE. Now I know the value of VE, which is 5.3 volts. So I can find out the value of the VC from here. VC equals VCE sat plus VE. So it would be 5.2 plus 5.3, 5.5 volts. So the value of the collector voltage that we got now is 5.5 volts, right? Okay. So now we see that our collector voltage is still less than the base voltage. Collector voltage is 5.5 volts and the base voltage is, what is the base voltage? The base voltage is 6 volts. 6 volts. So our base is still higher, 0.5 volts higher as compared to the collector terminal. So our collector to base junction is forward biased. and our BJT is in saturation, right? So these numbers make sense and our assumption makes sense now. Okay, so we ended up finding the value of this VC, which comes out to be 5.5 volts. Now, so we can find out, we can again find out the value of the collector current now. New value of the collector current with this correct value of the VC voltage. So our collector current now should be equals to, solving again for this, 10 minus VC over RC. 10 minus VC 5.5 over RC 4.7K. The value that will come out to be 0.96 milliamperes. So once we find out the value of the collector current, now I think the only value now that is remaining is the base current. Right, so we have a value of the emitter current, we have a value of the collector current, collector voltage, emitter voltage. Now let's find out the value of the base current. Again, we know that emitter current equals base current plus collector current. So the base current will be emitter current minus collector current. What is the value of the emitter current? Emitter current was 1.6 milliamperes, 1.6 milliamperes, and the collector current is 0.96 milliamperes. So 1.6 minus 0.96, our base current will come out to be 0.64 milliamperes. This is the value of the base current. So with that, we ended up solving the circuit. We ended up finding out all the values of the voltages at the nodes, emitter, base, and collector. We also ended up finding the current that is flowing through the transistor. Let's also see what is the value of the beta here, since we were not given the value of the beta. So the beta forced, again, beta force is the value of the beta, common emitter gain, in the saturation mode, which would be equals to IC over IB. The collector current is 0.96 milliamperes, and the base current is 0.64 milliamperes. So once we divide these two values, the value of the beta that we got is 1.5. Now you can see that the force beta equals 1.5. And this value is significantly smaller than the value of the beta when the transistor is operating in the active region. And again, why, kind of a conceptual thing here, why the value of the beta in the saturation region is smaller? Because our base current increases and the collector current decreases as the collector to base junction moves from reverse bias condition to the forward bias condition. Okay, so this is good. Let's do one more example now. Okay. Okay, so we have another circuit. Again, we want to find out the node voltages. So we want to find out what is the value of VB, what is the value of VE. VE is 0 volts. We can easily see over here. What is the value of VC here? Okay. So this is what we wanna solve for, right? And we know that the value over here is VBE equals 0.7 volts. So again, we are starting from exactly the same assumption. Our emitter to base junction is forward bias. It is 0.7 volts. Since emitter terminal is grounded, our base is at 0.7 volts. Okay, so if our base is at 0.7 volts, if I know the value of this VB over here, I can easily solve for this to find out the base current. So our IB now equals 5 volts minus VB, which is 0.7 volts, divided by RB, 100 kilo ohms. So the answer that I will get is 0.043 milliamperes. So this is the amount of the base current that is flowing into the base terminal of this NPN transistor. Now again, before moving to find out the value of the collector current and the collector voltage, we need to make an assumption. And we can always start with the same assumption. Assume BJT is an active region. Okay, so we have a value of the beta given as well. So we know that the beta equals IC over IB. I know the value of IB and beta, so we can find out the value of IC. Collector current equals beta times IB. Beta is 100. Base current is 0.043 milliamperes. So value of the collector current comes out to be 4.3 milliamperes. Okay, so we ended up finding the value of the collector current. Now I have a value of the collector current. I know the resistance. I have this value. If I will just solve for this thing, I can easily find the value of the collector voltage. So if I apply the Kirchhoff's voltage law, our VC will be equals to 10 volts minus ICRC. So it will be 10 minus IC, 4.3 milliamperes into RC. RC is 2 kilo ohms. So the value of the VC that will come out to be will be 1.4 volts. Now let's verify if our assumption was correct or not. So if we look closely, our collector voltage, what is our base voltage? Our base voltage was 0.7, our collector voltage is 1.4. So our collector voltage is at a higher potential, 1.4 is at a higher potential as compared to 0.7, and the difference was 0.7 volts. So this means that our collector voltage is 0.7 volts higher at a higher potential as compared to the base terminal in this NPN transistor, which means that our collector to base junction is reverse biased and BJT is indeed operating in the active region. So our assumption was correct. Okay, great. So we ended up finding out the value of the emitter voltage, the base voltage, the collector voltage. We have a base current, collector current. I think the only thing that is left is the emitter current now. Okay, so our emitter current equals base current plus collector current. So the base current is, what is the base current? 0.043 milliamperes plus collector current 4.3 milliamperes. So once we take a summation, the value of the emitter current comes out to be 4.343 milliamperes. This is the value of the emitter current that we find. Okay, great. So this is how we can solve this example as well. Okay, so let's do a slightly more complicated. Again, essentially it's not a complicated example, a very kind of a similar thing. So let's solve another circuit, more importantly. So again, we need to solve the circuit. We need to find out the node voltages, the branch currents, and the beta is 100. If we look closely, we essentially have solved this circuit and the transistor many times, except for this thing, right? So we have these two resistors extra attached as compared to the earlier circuits that we have just done. So what I'm going to do is, now I'm going to simplify this base circuit. So the first thing that we should do is simplify base circuit using Thevenin equivalent. So how will that look like? I'm gonna have this resistor. So this will be my VBB, this will be RBB, RC plus 15 volts, RE. Okay. So this is how it will look like as a Thevenin equivalent circuit. Now I need to find out the value of the VBB and RBB. So if you will remember your earlier courses, we can very easily find it out. The value of the VBB will be equals to, you have a supply voltage here, 15 volts, into RB2 over RB1 plus RB2, 15 over 100K over, sorry, 50K over 50K plus 100K. So if you will solve this, the value of the VBB will come out to be 5 volts. Okay, so this is equals to 5 volts. Okay, great. Now the second thing that we need to find out is the equivalent resistance. Both of these resistances will appear in parallel. So RBB will be equals to RB1 in parallel with RB2, 100K in parallel with, what is the other one? 50K. 50K. So if you will simply solve this, 100 into 50 over 100 plus 50, the value that is going to come out to be for RBB will be equals to 30.3 kilo ohms. Okay, so we have these two values here. All right, now if you will look at this circuit, and if you will look at the previous example circuit, the circuits looks exactly the similar, right? So we can exactly use a very similar approach to solve this thing. Okay, now we can again, what we will do is we will make an assumption of an active region operation, and then at the end of the day we are going to verify it if this is indeed transistor is operating in the active mode or not, right? So let us start with assume active BJT operation of operation region. Okay, so if I will do one more thing, I know that the value over here is plus minus VBE, and the base current is flowing over here, IB. All right, so let's consider this loop. If I will solve for this loop, I can write down this equation. VBB equals IB base current into RBB plus VBE plus IE RE. Now I need to solve this equation to find out the value of the emitter current. So first thing that I will do is, so that I will have one value, one variable of the current over here, I can replace this IB by IE over beta plus 1, this equation. This is the equation one that we derived in one of the lectures in the first week. Okay, so let me put this value over here and rearrange this equation. Okay. So I have VBB minus VBE equals IE RE plus IE RBB over beta plus 1. So we can take the IE common from here. So IE can be taken out as a common. And what we are left is RE plus RBB over beta plus 1. Okay, so we can find out the value of the current, IE. So let me write down this equation in the next slide so we can also put down the values. IE equals VBB minus VBE. VBB minus VBE over this RE plus RBB, over beta plus 1 over beta plus 1. Now we have a value of VBB which is 5 volts. I think we have all the values now. So 5 volts minus 0.7 volts over, what is the value of RE? 3 kilo ohms plus RBB is 33.3 kilo ohms divided by beta was equals to, I think, 100. So it should be 101. Okay, so if you will solve this equation, the emitter current that will come out to be equals to 1.29 milliamperes. So this is the value of the emitter current that will come out. Again, we can replace this value in this equation here and find out the value of base current. So the base current was equals to IE over beta plus 1. So 1.29 milliampere over 100 plus 1, it will come out to be 0.0128 milliamperes, a very small value of the base current. Okay, so we ended up finding the value of the base current and the emitter current. Now let's find out the value of the, we also have to verify the assumption as well, right? So let's find out the value of the node voltages here. So the value of the node voltages, okay, so we know that our VBE equals 0.7 volts, which is equals to VB minus VE. Now we know that, what is the value of VB here? If I have to find the base voltage, VB equals VE plus VBE. And the value of VE, looking over here, right? So the value of the VE is over here. VE is over here, which is equals to IE times RE, right? So VE equals IE RE. So IE RE plus VBE. So the value of IE is 1.29 milliamperes. The value of the resistance RE is 3 kilo ohms. Plus the value of the VBE is 0.7 volts. So once we write down all of these values, the value that will come out to be should be equals to 4.57 volts. So this is the value of the base terminal voltage that we ended up finding. Okay, so the next thing that we need to do is to find out the value of the collector current. Okay, so because in order to find out the value at the collector voltage, we need to find out the value of the collector current, and then we can compare this collector voltage value to the base voltage value and verify our assumption whether it is true or not. Okay, so in order to find out the collector current, we can, for example, use this formula, IC equals to alpha times IE. Do we know the value of alpha yet? No. So one thing that we can do is, we know that alpha equals to beta over beta plus 1. Have you used this thing? So you can find out all of these alpha and beta relations in the first week lectures. Let me quickly show you where they are. Right, so when we are deriving this emitter current equations, we ended up finding out all of these expressions. For example, here's an expression of alpha. Similarly, you can also find out this beta and alpha expression too. So it's beta over beta plus 1 is alpha. Okay, so beta over beta plus 1. So again, alpha equals beta was 100 over 101. So it will be 0.99 would be the value of alpha. So we can put down this value over here. The value of the collector current will come out to be 0.99 multiplied by IE. IE is 1.29 milliamperes. So the collector current will be equals to 1.28 milliamperes. So this is the value of the collector current. So now we know the value of the collector current. Now we can easily solve this equation, this circuit now, or this using Kirchhoff's law. So the value of the IC will be 15 minus ICRC, right? Okay, so value of the VC, yes, okay, VC equals the biasing voltage, 15 volts. So 15 volts minus ICRC, 15 minus IC is 1.28 milli into RC is 5K. So if you will solve this equation, the value that will come out to be 8.6 volts. Okay, so this is the value of the collector voltage. Now let's verify our assumption. Our collector voltage is 8.6 volt. What is our base voltage? Our base. Okay, this is the base voltage that we ended up finding out, 4.57. So our collector voltage is 8.6 volt, base voltage is 4.57 volts. This means the collector voltage is greater than the base voltage, and the difference is 8.6 minus 4.57 equals 4.03 volts. So this means that our collector terminal is at a higher potential by 4.03 volts compared to the base terminal, which means that collector to base junction is reversed bias and our BJT is in active region of operation. So this verifies our assumption and this solves this question as well. Okay, so this was the last example that we are going to do in today's lecture. We have one more example problem which is slightly more complicated that we will do in the next lecture, in which we will have multiple transistors, NPN and a PNP transistor combined together in the same DC circuit. We're going to solve that in the next lecture. Again, in order to solve any of these problems, you can always consider these very basic circuits. Our emitter to base junction in both transistors NPN, PNP, in both regions of operation, active and saturation, emitter to base junction is always forward biased, and we can replace that with a 0.7 volts constant voltage drop model of a diode. The other thing to note over here is our collector to base junction should be reverse biased. This means that for an NPN transistor, our collector should be at a higher potential as compared to the base. And we have seen that for our common emitter model, our collector to emitter voltage should be greater than 0.3 volts for the collector to base junction should to be reverse biased. So when this collector to emitter voltage will decrease and will become equals 0.3 volts, this means that it is the edge of saturation. And when it further decreases, and this will mean that our transistor is in the saturation mode now, and our collector to base junction is forward biased. And the value of the VCE in the saturation mode equals 0.2 volts, right? This one. And in that operation, our transistor, beta value of the transistor, or the common emitter gain during that region of operation, in the forward saturation region of operation, is forced beta. And the forced beta is IC over IB. And this is always less than the beta value in the active region. Why? Because our base current is increasing, collector current is decreasing in the saturation region. Then we did a bunch of these examples. Again, you can always start with the base to emitter junction to be forward biased with a 0.7 volts, find out those node voltage values. Before finding out the collector current or the collector terminal voltages, you need to make an assumption. You can always start with the active region mode of operation assumption and then find out the values of the collector voltages and compare that value with the base voltage. And if that value is larger than the base voltage by 0.4 volts, this means that it is at a it is reverse biased. Collector to base junction is reverse biased, and the NPN transistor is in the active mode of operation. And as soon as this voltage will drop, if the base terminal is at a higher potential as compared to the collector voltage, this means that our collector to base junction is forward biased, and since our emitter to base junction is already forward biased, so it should be a saturation region of operation. Okay, so with that, we are going to end our today's lecture, and I will talk to you in the next lecture. I hope that these examples will be helpful for you in using the concepts that you have learned so far and further analyzing and understanding these circuits more. Okay, all right. Thank you so much and have a good day, all of you. Bye-bye.